Hello, welcome to our semiconductor education program. I'm Vincent Chang. With a good understanding of the concept of input offset voltage and also the experience of solving a BJT differential amplifier's offset voltage, now you are in a good position to move forward to solve an input offset voltage of a MOS differential amplifier. Input offset voltage MOS differential amplifier. What's the first step? When you face the input offset voltage issue of a differential amplifier, what's the first step? DC grounded. The input terminal should be DC grounded. Let's now assume the first issue is load mismatch. There's a difference between the two drain resistors. The difference is delta ID, RD. And then the same, 50-50, the same. So you can get the voltage, the differential out. I skipped one step. You should be no problem with this. With the experience you have the bipolar differential amplifier. And then what? I also skipped the explaining the origin of the finding the differential gain, the GM. I assume you are very familiar with this. And then what? Transconductance of the MOS transistor. Transconductance of the MOS transistor. So maybe just pause. Put down the relationship, square law relationship. ID equals half K, MOS, the K of the MOS, parenthesis VGS minus VT. What T? Thermal. No, threshold. The threshold voltage square. Partial ID, partial VGS. Derivative. So K, I hope you can follow me. VGS minus VT. And also half IQ in terms of VGSQ is the square law. So a lot of stuff got canceled. K VGS minus threshold voltage got canceled. So here's the answer. The first offset voltage, half overdrive, half. You want to put this on your note. Overdrive. What do you mean by the overdrive? The driving voltage VGS, the part over threshold voltage. If the threshold voltage is 1 volt, VGSQ is 1.5, and 0.5 is going to be overdrive. So half overdrive, fractional change. Half overdrive, fractional change. The second issue, mismatch. Let's say K mismatch. Because K equals what? K equals what? Equals mobility, gate oxide capacitance times channel width, W, over channel length, L. Geometry mismatch, geometry ratio mismatch, W over L mismatch. The total variation between two sides, the two transistors, is delta Kn. Up a little bit and down, on the right hand side down a little bit. Then the current will be different. The left hand side, I explained this in the previous lecture video when we deal with the bipolar, so I don't have to belabor everything, all right? So just try to follow my pace. So ID1 is going to up and down. Also, boom. The left hand voltage, right hand minus left hand. VD2 minus VD1. VDD got canceled out. So ID2, RD pull out. Then the difference between two current. When you take the difference between two current, half IQ got canceled out. This is the answer. Same thing. So you can expect the similarity is coming. half overdrive fractional change, right? Half overdrive fractional change. The third one, the third offset voltage, let's say threshold voltage mismatch. The difference between two threshold voltage is delta VT. Half on the left minus half on the right. The total difference is delta VT. Let's start with this. This is might be a little bit complicated for you. Half Kn VGS minus VT. Plug in the VT1. VT plus delta VT over 2. Plug in the VT1. Then pull out the regular factor VGS minus VT. Pull this out. And then what? Then let's assume it's the parabola, it's a square law. But let's assume the delta VT is very small. Then the second order term is negligible. The second order, constant first order, the second order term is negligible compared to the first order term. Then you just keep the first order term. Right? So here's the ID1. So in the same way, you can lay out the drain current of Q2. So do you think this makes sense? You can also do this more instantly. I mean, when VT up a little bit, ID1 should what? Should down a little bit, minus sign, the blue equation. When VT2 is down a little bit, smaller, therefore, the ID2 should up a little bit. So intuitively, for this reason, these two equations make sense. Then what? Then it's easy. VD2 minus VD1. VD2 minus VD1. Plug in. And then it's this. And then differential gain, transconductance. You see? Delta VT. Are you with me? Are you with me? I mean, K times overdrive is transconductance. RD canceled out. It's delta VT. Super simple. It's very simple. Beautiful result. Here's the takeaway. Load mismatch, half overdrive, fractional change. Geometry mismatch, K mismatch, half overdrive, fractional change of K. The third one, VT mismatch, delta VT. Very simple. I encourage you to do a little bit of juxtaposition. I mean, just go back to the bipolar impulse voltage or bipolar. Take out bipolar. Do a juxtaposition. Contrast. Load mismatch. The same. Delta RC over RC, right? Half overdrive for the MOS correspond to what? Correspond to what? Thermal voltage. Half overdrive correspond to thermal voltage. Same thing with geometry mismatch. In bipolar counterpart, it's the delta IS mismatch. So delta IS mismatch corresponds to delta K mismatch. Half overdrive corresponds to thermal voltage. So I encourage you to do a little bit juxtaposition and do a contrast between bipolar, and MOS, right? This is the end of the lecture video. I hope you enjoy it. Thanks for watching.